Okay, so today I'm going to start off talking about the microprocessor on where we started this project 2 on what, Monday, right? And then we'll finish this up next week and we'll start lab 8 next week also, which is more state machine stuff. So I'll finish off after I talk about microprocessors, going back and talking about state machines again so that we don't forget all about those. Okay, so this microprocessor is a little bit different than the one we were working on building in project 2, but it has a lot of the same ideas, right? So this one, the black, anywhere you see the black is going to be on the bus. So we can consider it like an 8-bit bus, right? This is our internal bus. It's the same type of idea that it connects everything together. Now, just like in our case, we have an ALU over here. In their case, so this is in the book, in like page 450, 451, something like that, if you wanted to go read the book's explanation, but I'm going to kind of walk through what's happening, right? So there's an ALU that's going to get some opcode, right? And then over here, R0, R1 are just registers that are acting as memory. So if I want to store values to use later, I store them in R0 and R1. Now we're going to use some external memory somewhere, right? But for now, this one, let's consider internal memories to the microcontroller, right? And so we won't talk too much about the control. This is what is represented by your test bench that is provided in project 2. So what the controller does is it sends out signals to perform various operations. So what do I mean by that? Well, let's do something like, if we want to add 3 plus 7, starting from scratch. Well, nothing is in these registers, so we're going to assert this extern signal, right? That tells this buffer that's going to some external data, like say coming from your test bench, right? That is going to say, you can drive this bus. Now you want logic that you can never drive the bus black from more than one source, because otherwise you're going to end up with conflicting data and potentially damage your parts. So where can that data come from? Well, it come from this R0, the R1 out, the external data, or the G out, which is just a register to store the results of this opcode. Okay, so we want to add 3 plus 7. It asserts extern, and it pulls in the data, and now this buffer, or sorry, this bus has that external value on it because it's been enabled. So then it would go and assert R0 in. That would allow it to store 3 into R0. So we put a 3 in the external, puts it onto the bus, we assert R0 in. Now R0 is clocked, R1 is clocked, A is clocked, G is clocked, and control is clocked. Okay, so at the first clock edge, it gets clocked, 3 gets clocked into R0. At the next clock edge, you want to have dropped R0 in, assert R1 in, and bring a 7 in. So now I've stored a 3 and a 7. Take me 2 clock cycles, right? Well, now if I want to do, now those are in those memories, I can do something with them maybe, but in order to say add them, I need to get it to the ALU. So what I might do then is assert on this signal, the A in, so that on the 3rd clock cycle, I will assert A in and R0 out. So that the bus is driven by this 3. That gets thrown into A because, right, A is enabled, A in. And then on the fourth clock cycle, I can put R1 out enabled, which has the 7 in it. Send a signal around to the B port. I should probably label that, right? Actually, let's call it X and Y since we have an A already. So 3 is in this A and is appearing at the X. 7 is on the bus and appearing at the Y. So all I need to do is on the next clock cycle, enable G in, right? Because this is combinational logic. It just happens as fast as it can, right? So then the clock cycle G in says, let's save X and Y. So G gets a 10 on it. Then on the next clock cycle, if I want to go back and store that, say I'm done with the 3s. Well, I enable G out, making sure that all of my other enables, right, my drivers are all off except for G out, and I turn on R0 in. So on the clock cycle, the 3 gets overwritten, and we store that 10. So that's how it works, right? That's the general idea of this bus. Now, I kind of mentioned in this lab, it's worth mentioning again, especially on video, that Vivado has a bit of an issue implementing this type of buffer, which is just an output enabled buffer, right? Where the ideal situation is if it's enabled, it's a wire, and if it's disabled, it's an open switch. Well, when we write the VHDL code for that, right, what do we say? Well, it would read something like, if I call this bus, let's call it B, gets assigned to R0 out when we call this, well, let's just call the signal R0. So it's equal to R0 when R0 out equals 1. Something like that, right? That would just be the buffer. But there's else statements, right? When else. So what is happening when else? Well, we don't really know. And by not saying, we're implying that we don't care. So what we do is else when, and I could leave off this, R0 out equals 0, right? I could just else this statement. It equals to, well, I don't say equal, right? I just say else a number of these equal to that. Okay, so that then is not really an output enabled bus, right? That's just a mux that uses R0 out as a driver, and if it picks 1, it uses that R0. If it chooses 0, it takes these. So that's what we're trying to do, more or less. Now, you could, in fact, in this case, in fact, it might be easier to write it as like a, like how we've written that memory interface module, right? We may want to write this as like a bus interface module, because we know that we never want more than one of those drivers to control that bus. So why not just take the same kind of mux and we could do something like R0, R1, G, and external. And then I could just add control signals, right? Which could be one hot or they could be controlled however you want. And now I have a mux that is guaranteed to never assert more than one of these onto the bus signal. If you want access to the bus, you have to come through this. And if I'm not driving the mux, then I just choose 0, 0, and I assert Z's. I'm not driving that bus at all, right? And it's just floating, which is an option. So anyways, that's the kind of idea that you want to do when you're driving the bus with the memory interface. Because in our case, we have the memory interface, right? And over here we have a memory. And they're connected together through in-out ports, meaning that I may need to write to memory, or maybe I'll read from that memory. So we make this memory interface, right, that has this kind of idea, this mux. And if we want to set, let's output enable. This is to or from the memory. And then this is internal bus, right? So what this is saying is I have some output enabled. If I want to drive this memory wire, I enable this. If I want to read from it, I turn it off. If I turn off output enable, it just looks like this, right? It's not connected, and it just functions as an input directly to internal bus. Right, and then we have to have something that tells eventually, the memory when it's okay to drive the internal bus. Because maybe we want to do that inside of the microprocessor, right? So alternatively, you could create an output enable on that one, but in this case, we're going to do it on the memory side in project 3. Okay, does everyone understand this? That memory interface? Okay, good. That seemed to be getting a sticking point for some people. Let me check my notes. What was next? Yes. So I'm going to talk about the controller now so that we're ready for project 3 when it comes. Okay, so the controller, it needs to know, based on some function input, what assert signals to go out, right? What flags am I setting? Who's controlling where? And so project 2 gave you a list to kind of give you this upcoming idea of what's supposed to happen for that controller. Now, let's say there's a bit of an issue, right? So we've talked about state machines. We want to go through a series of states in order to control what's happening in this microprocessor. All right, so let's say we want to add a value from memory, say R0, to the external, right? Well, first we have to load into memory. And so if we load into memory from this, so we would say external gets asserted and R0 in gets asserted, right? One step, one clock cycle. Well, the next command would then be, well, let's put, actually we could skip that, right? We could put it directly into A. We could say put into A. And then the next one would assert the external signal and put it onto Y. And now I'm adding 2 numbers, right? Each in one step. But now the add operation gets a little bit interesting, because if I want to store that value, 2 things have to happen. First, I have to save the value in GN, and then I have to save it to one of these memories, right? So I may have a command that says add and then store. But some of our commands are going to take 1 clock cycle, and some of them are going to take 2 or even 3 clock cycles. So this one, actually, this architecture is pretty good about doing most of their commands in 1 clock cycle. But ours is not necessarily that good. Let me see if I can think of one that is a good example. Yeah, so ours, if we want to add 2 values, we have to load one of them into this accumulator first, right? We have to load, and then we can add, right? I can't do 2 numbers in just those clock cycles. And then if I wanted to store it to memory, that's another one. So our state machine, when we start thinking about the control, we're going to start in idle, right? We're going to hang out waiting for things to happen. And each rising edge of clock, we're going to evaluate what state do we go to next. But we could go to lots of states, right? Depending on what our function is. And we've been given a list of functions in project 2 to know what's coming. And so, like, if the function is equal to load from memory, LDM, right? Well, that has associated with it, what does it have to do to load from memory? Well, it has to turn off OE, right? It has to send a signal that says, hey, memory, I need something. So that would be like the equivalent of this extern signal. And it has to send out the opcode load, right? So let's do this. I'm going to stick with calling that. You guys in the lab called this write, I believe, right? W. So in this state, in LDM, I need OE equals 0. Extern, yours is like going to be like, well, I think you just used not write, actually. So write equals 0, extern equals 1, saying, hey, go ahead and give me something. Opcode equals load. Is that all? I think that'll do it, right? Oh, and PC equals 1, right? So I want to go on to the next command because I'm good with that. I'm done. That's load from memory. Store to memory then, right? So if F equals STM, store to memory, then I have to think about what does that mean? Well, we go to the state STM. I have something in the accumulator. So I need to say, okay, well, on the first clock cycle, I'm going to assert write. Extern would be 0. Opcode is what? If I'm trying to save this accumulator off to memory, what do I do with the ALU? Just hold, don't do anything, right? Keep that value inside of that memory so it has a chance to write it. Okay, so I'm writing to the memory, a clock cycle comes along, the clock cycle happens, ACC updates with itself, it's no problem, and memory updates with the next value. But after I get that code, there's a good chance, I believe this is one, where it actually takes 2 clock cycles. You need to do the setup for the hold and then the next clock cycle. I'd have to go back and double check which ones take 2 clock cycles. In fact, I think many of them do. If you go and look at your I can't think of the word, test bench that is provided in project 2, right? It says things like, there's a comment that'll say PC equals 0, 0, and it has a bunch of code, and then it says PC equals 0, 2, I think is the next one. And then in that, there are 2 lines, and the next one are 2 lines. But sometimes there's going to be a clue that if in one of these commands, the inc PC equals 0, that's your clue that that command is going to take more than one state, right? So what I've provided for you, this test bench in project 2, is a strong clue as to how you're going to have to make this state machine. This state machine being the controller, right? Because anytime you have a controller, it needs a state machine. That's how we build that. So this is the general idea. We're going to go to these states and assert these relevant signals so that it accomplishes the goal. In order to be able to design that, you need to understand, how does this work? What is those commands that we're trying to give to accomplish add? What happens if I say function add or function load, store to memory, right? What do those mean as far as those control signals go? Figure that out, create a state to do it, you're good to go. So the ALU and our accumulator, I'm gonna go through this real quick. Right, this is pretty self-explanatory. This is just a register of D flip-flops, right? A couple different ways to do it are, this can either be 8, and then you'd have an extra for the most significant bit that is carry, right? This is carry out, C out. And then that makes this 9 bits, this 8 bits in the feedback, and we just tap 1 out to go into the C, right? Or you could just make this 9 bits and get rid of the C. Several of you did, there's a couple different ways to do this accumulator. Neither is wrong, and in fact, kind of one of them requires more work, but I actually kind of like it. So one of them is to write the code for 9 D flip-flops, then use like a generate statement to make 9 of them, and then you've made it. Also, you could just do something like process on the clock. If this is F and this is R, then you would just say right, that's all. Is each clock cycle assign R to whatever's on F. This implements a register. So you don't have to write the D flip-flops. You can just do this. Okay. The output register was the next part of project 2, right? Which I drew up there. I already did that one, right? Which is just the when else statement on this driver. Making sure, this is actually one of the weird things I will point out. When you write Z's, you need the right number of Z's for however big your bus is, so 8 or 9. And they have to be capital. It doesn't like lowercase z's. This is one case where like capitalization matters. It's kind of a weird thing. And anyone, if you haven't gotten far into this project, the important thing is when you're looking through all these figures that are in that project, is just to follow the names, right? So like if internal bus is here, in this figure, it's also here. That means they're connected, right? So it is possible to draw a full diagram of how all of these things are actually connected, and that is very useful to do. And remember that when you design like a new mux, right? So this mux here, I'll replace it. You don't have to go and make a new mux with port names of Z and R. You've already made several, I assume, 2 input muxes, right? And their ports are like A and B. Don't go make a new mux. Just go take the code that you've already written and then just do the port mapping of Z and R into it, right? This is something we want to talk, like, remember, is we can reuse this code. We don't have to write a new mux every time. We can just use what we've already done. Similarly, there's another issue that students run into with muxes in general, where you're supposed to, the mux is literally just a switch, right? So internally, there's like a switch and it just flips back and forth between one or the other and just makes that connection. There's this weird tendency of students that I'm still trying to understand, and like, I don't fault you for doing this because it's just so prolific, that instead of treating it like nothing more than a switch, they try and do this thing where like internally, there's like, let's say we were designing the mux that we did for your initial ALU, right? So I have add and add C. What a lot of students will do is they'll be like, well, there's an A and a B input, and then they come into the mux, and then they get mapped like this, and then there's an output, and then, oh yeah, here's another mux or something, right? And they like, you try and shoehorn the components into the mux. A mux is nothing more than a when else statement. As soon as you start putting other logic into the mux, it stops being a mux and starts being an ALU. Right? So don't overcomplicate your mux. Don't overcomplicate any of your components. That's the beauty of VHDL, is you never have to understand more than one level at a time. It's just build a mux and then connect it to a buffer, right? And a buffer, like in this case, is just saying, what do I call this? I'll just call that signal M for now, right? That's a buffer. It's a D flip-flop if it's in a process, so be careful. If it's combinational logic, that's a buffer. That's one of the things you have to be careful about. Inside of a process, this is a D flip-flop. Outside of a process, it's a buffer. Okay, so what that will do is this signal, IB and M are the same, but it's allowing us to create a port for IB, which is just an output, and a port for M, which is an in-out, right? It's turning an in-out to just an out, because this may be tied to R instead. That's why we want this buffer here. That's all it takes, is that outside of a process. Okay, so then the last bit that is pretty confusing is the PC and MAR. And again, we have a mux. I've seen too many students trying to write a whole new mux that has inputs called MAR and PC. Don't do that. Make ports A and B that map to MAR out and PC out, right? And then we have like this thing called fetch. Okay. And then here, once again, we have the internal bus. Okay. So what this does is the PC. We'll start with the PC. We're driving this microprocessor from addressable memory, right? We just had a question on that on the exam. We did it in the review, which is basically going to be more or less a list of commands where we are, the address, right, is determined by generally PC. But calling this PC is a little bit confusing because it's really ADDR, right, address. So for address 0, I get whatever value is in here. This value can be a command, or it could just be a value to add. It could be either one. And we have to kind of know what that is. So let's say we start up this program. The PC is going to start at 0, no matter what, right? And PC has a couple values. It has load and increment. And MAR just has load MAR. Okay, so the loads are just parallel loads. What they do is if they're asserted, they bring in whatever value is on IB. Why would you do that? Well, let's say the system wanted to start at somewhere that wasn't 0. Well, my counter starts at 0. Well, the first command, I have to do something at 0. There's no other way because I don't have a way of asserting load command. So I could do like jump to 2 or something like that, right? And the first thing that happens is, well, jump, we know, asserts, well, I don't know that you know this yet, but what it would do is my goal is I want to get my address to 2. So what it does is it says assert load. Actually, this is a really interesting example. The first thing that it has to do is it needs to get that address 2 onto this internal bus, right? So the first step is from memory, it pulls out address 2 and puts that on the internal bus. Without incrementing the process controller, but going on to a different part of that state. So this takes multiple states to do. We have to then load that address into PC. And then we can start counting. Now our PC says 2, we select fetch, we have 2, we jump down to here. We've ignored whatever this is, right? And now I'm sitting here and now I can do like add immediate. Well, add immediate says right after this clock cycle, the memory is going to provide a value for you to add to whatever is currently in the accumulator. Well, I just started, so the accumulator is 0, so I could also send the load command. But so add immediate, load immediate is pointed at the same in time, add immediate, and then this might have something like 4E, right? 8 bits. So we go step, loads that 4E, it's now in here, and we step along. Now, the MAR, we may then say, I want to add something else. 21 or something, right? And then I want to store the result of that to memory. I need to remember that value, and I'm going to give it a location, say 8. But that means I'm storing a number in 8, and I have to do something with it, and that may be jump over it, or it may be, right? So what happens is we're stepping along in the process counter, add 21, store it to 8. Okay, store it to 8 is going to pause the increment PC for a little while because it needs to do a couple of things, right? It needs to take whatever in the accumulator and go throw that into memory. Sorry, I just got distracted. To do that, it's not going to use the process controller load. What it's going to do is use the MAR, the memory address register. That's what this is doing. This is remembering for you where to store something in the future or in the past, right? Go somewhere else that is unrelated to the process controller, store it, and then we can come back to PC without having kind of just kept on counting. Does anyone understand that purpose for the MAR? Is so that we can do that. And then if we've stored that value in here, whatever that value ends up to being, we would just jump over it and keep going. And then that MAR, if we wanted, we could just change fetch to 0 and go back and get it. Right? It's waiting for us. This address of the memory is waiting for us to use later.
So when you say store 8 and 6, is the MAR remembering 6 or 8?
The MAR is remembering 8 because the process counter is 6.
Okay.
The location that I want to store to is 8.
Okay, and then if you ever wanted to fetch that, that number again, you just have fetch equals 0, and your address would go back to 8 to grab that value.
Exactly.
Okay.
Yeah. Yeah, so it fetch 0, that MAR, until we update it. And maybe we could also store that address somewhere if we wanted to go back and do it later, right? We can store the MAR if we wanted to. Not from the MAR, we'd have to store it at the same time we put it into the MAR roughly, otherwise we kind of, because this has no, address has no connection to the internal bus. So that's a bit of an issue, but you could store an address that we're gonna like, hey, we're gonna keep storing and using this address and just throw the address into memory. So this memory, the addressable memory, functions both as a list of commands and a storage block for all of your data that you're going to use. A lot of times, especially early on, what you're going to do for that is you're going to like the end of the memory is reserved for the storage, and the first part is just your execution list, things like that. But this is why addressable memory is important, is understanding this, right? And I'm going to erase this. I think I'm done with that. It's addressed at the simplest level by a decoder that just takes address, right? And a decoder's whole job is it gives an address and asserts exactly one of these outputs. And when that address is asserted, remember that AND gate diagram that I drew, it sends those bits out and you have now access based on its decoder. That's all it's doing. This is why it's important. Okay.
So the MAR just stores the most recent value that you have, correct?
Yes, whenever the last time that you asserted load MAR, whatever was on the internal bus will get stored in it, and then stay there until the next time you assert load MAR and have a rising edge of the clock cycle.
So when you assert load MAR a second time, what happens to that address that's previously in there? It just disappears.
It's gone.
So if you wanted to access that value again, what would you have to do?
You would have had to have recorded that address in the memory somewhere.
In memory, and then go fetch that directly from memory.
Yes, and then you would say load from memory, LDM, that location.
Okay.
Now and then the next clock cycle. So that location, load from memory, would store a location, right? So let's say here we had ADDR, what did I say, 8. So line 9 of my address has the address for 8. So the first thing that I have to do is I send load from memory. And what that does is it puts the address into the accumulator. Because that's by definition what load from memory does, is it takes whatever's in the memory and stores it in the accumulator. The next thing that happens is we set write to 1 so that we're R. That feeds back R, the contents of the ECE, to the internal bus. Now this time we don't tell the memory it has to do anything. because we don't want to put that memory address back in. We just take this, we want it back on the internal bus. Now it's appearing on the internal bus, and of course, as soon as I said I don't need it anymore, I need it. This is internal bus, right? And now that's tied to that output, which is tied to R. So the value, that address 8, got stored in this accumulator, now appears on the internal bus. I assert load mar, and the clock cycle happens, and I store that value into the mar. And now I can use it again.
That makes sense.
Okay, good. Okay, any other questions on the microprocessor at this point before I transition to state machines again?
I have a quick question. So VHDL, how do we design the MAR PC?
Well, the MAR is just a register, memory address register.
Oh, okay. Just register.
So it's just Q equals D, right? If rising edge of clock and load MAR, Q equals D. Done. The PC is just a counter with parallel load, which we've designed counters for homework, right? So that's all.
Okay, thank you.
Yeah. Where Inc PC is the count enable. If Inc PC is true, count up. If it's not true, don't count up.
Okay.
Yeah. Any other questions? Okay, I'm going to start erasing then. Okay, so state machines. State machines are very important. These are how they control any type of thinking machine. Now, state machines are used not only in hardware programming, which this is, right? Remember, it's important to remember that in this class, we are programming hardware, which is slightly different than programming software. That being said, state machines are used as often in software as they are in hardware. They're ubiquitous. The main idea being, almost always you're going to have some start state. There's usually an arrow. Well, I say usually, I rarely remember these. That says start, that says this is where when you turn the system on, you go. And that would be done by saying if reset state goes here. Okay, so the next thing that we do is we create that beginning state. What are we doing? And then the one that I used, right, was the stoplight initially. Like we're at a red light, something happens, we go to green, something happens, we go to yellow, some amount of time goes by and we go back to red, right? This being the state machine diagram. Now, there was also the state table. The state table contains the same type of information in table form. Now, the diagram, the bubbles are usually easier for us humans to read, but the tables are easier to implement math from. Okay, so the things we need to know is where are we right now? What is our current state? Then based on that, what is our next state? Where are we going? And that depends on what our, not only where are we now, but also what is our input, right? So we may have inputs of A and B in this case. And I'm going to just go ahead and list them. So we're going to have states. I'm going to have 3 states, 0, 0, 1, 0, and 1, 1. And that's going to have inputs of A, B. And there are 4 possible combinations of this AB input, right? 2 bits means 4 combinations. So I have 0, 0, 0, 1, 1, 0, 1, 1. And then we just answer the question, where do we go based on where I am and what that input is? So, and I'm just going to fill up like an example table here. Okay, so what this is saying is if I am currently in state 1, 0, then I want to, and the inputs are 0, 1, then I go to state 1, 1 next. Everyone gets that, right? I hope. Okay, the next thing is we have some output. And it too depends both on what state are we in now and what are our inputs. Right? So this is just saying if I'm currently in state 1, 1 and I get an input of 0, 0, I go to state 0, 0 and my output is 1. Right? That's what this is saying. This is not quite a complete state table. Why? What am I missing?
Current state 0, 1.
Yes, exactly. Current state 0, 1. I only use 3 states, but with 3 states, I need 2 bits to represent it. That means I have an extra state that I'm not using, but it exists. What do I do that for next state? What is the next state for 0, 1?
You don't care because you're hoping to never get to 0, 1.
Exactly. If I'm there, I have a problem. Whole bunch of don't cares because I'm not supposed to be there. Now, you could tell it if my next state is no matter what, 0, 0. So if something weird happens and you end up in that state, just go back to the beginning. But generally, that's not what you would want to do because you kind of want the system to break if that happens, because it's easier to debug if it actually does break, right? Instead of just like, why did it reset? Okay, so now we have this table. You can and should go ahead and do it. Draw me this diagram, this state diagram from this table. Right. Start by drawing state 0, 0. Draw its arrows where they go based on the inputs. Make me a state diagram of this.
Where would you specify the starting point? Does it matter?
Generally 0, 0. There's a lot of reasons to start at state 0, 0. Well, there's like 2 reasons, but yeah. Unless told otherwise, start at 0, 0. And actually, this reminded me, whenever I start doing this, remember that you can have both a state assignment number, which is required, right? We have to represent with the states with numbers. But we could also just give them names. That makes it easier to write in code, right? In a VHDL, we do that by writing a constant. Here, we just add an extra column that says something like, well, I don't want to use A and B because those are my inputs. So instead, let's go ahead and give them names starting at M. No, well, whatever, I'll start at P because I hate O as a variable. P, Q, R. I'm not going to give 0, 1 a name because it doesn't appear in my state diagram, right? Because I don't use it. So instead of writing like this weird sad head or something, I can P. Okay, I think this is right. So, well, and it's not quite complete yet. So what I do is I just started at P and I drew all of the possible next states, right? So I drew P, Q, and R, And sometimes you're gonna want to go back and redraw this, especially as you start to get more than like 5 states. 3 states is easy. It's hard to screw that one up regardless of where you put them. 5 states, you can start getting really weird, messy ones. But I went ahead and said, what happens if I go 0, 0? Well, 0, 0, I go to Q. 1, 1, I go to R. Oops, did I mess that up? I did, because I can't read my own handwriting. So 0, 1. Oh, wait, sorry, I did that right. 0, 1, I go to R. 1, 0, I go to P. They put 1, 1, I stay in P, right? Okay. The next thing that I have to do that I haven't done, and so I did that for all 3 states, is I just wrote all of the arrows for my possible next states at each of the states. What I haven't done is assigned the outputs, right? And that's what that dash is, input / output. So outputs are 0, 1, 0, 1. So 0, 1, 0, 1. Right? And then I would go and assign all of the remaining outputs there. Scroll this over a little bit. There we go. Okay. So that's how we would go from a state table to table to diagram. Very fair and valid test question. I will assign some homeworks that do stuff like this. I'll try and get that assigned today. Okay, so now I have a state table, I have a state diagram. I want to design the actual logic that implements this state machine, right? Now, you can kind of go at it from either the state diagram or state table, but as I said, it's much easier to map stuff, design stuff from the state table than it is to do it from the state diagram. So I'm going to go ahead and erase the state diagram because it's not going to be particularly useful to us as I step into the design of it. So there are 2 different concepts that I need to design logic for. There is the next state logic and the output logic. We also call them the next state decoder and the output decoder. And what that means is we are decoding an output based on what are our inputs. Okay, so let's start with the easy one, the output. And if I call the output Z, so I don't have to sit and write out, what do I do? What tool do I use to begin the design for Z as our output logic? What's the first step in designing this?
You're talking like VHDL?
No, we don't want to jump right to VHDL. We want to do some thinking first. How do we design logic? How do we design good logic?
I know map.
K-maps. Perfect. This guy apparently decided to try and give up. Great, I have a K-map. What are my variables? What do I care about? What are my inputs into this logic? A and B, absolutely. I do a 4 input. What are my other 2 inputs?
Next state.
Yes. And what are they? Well, we have 2 different bits, right? Where we have these current state bits that are 2, and we have next state bits. And we have to decide, we're trying to make the output decoder that cares about 2 things. What are the inputs? And what state am I in now? So it's really our current state. Close, but it's our current state that we care about. So our current state, we're going to call Q1, Q0. Our next state is D1, D0, just for reference. Right, remembering, which you probably don't, but that's okay. Our current state is stored in D flip-flops, right? The next state decoder is combinational logic that takes the current state and our inputs, and our output decoder takes our current state and our inputs. Remembering that this one is actually optional. Right? Why is it optional? When do we not use this path? There are two types of state machines, Mealy state machines and Moore state machines. Mealy cares about, the output cares about both the current state and the input. Moore state machines only care about the current state. Okay, so the next thing, as I said, so this is our map for Z, the output. Now, the way I do this is I just look at the table and I can say, well, if my Q1, Q0, 0, 0, and then my output is 0, 0, I get 0, right? Well, now I've got 0, 0, 0, 1. That's this spot. Where is that? Well, Q1, Q0 is 0, 0, 0, 1. 1. Well, now after doing that one, I only need to do that one spot to see where I'm going, right? The direction. So now I can just start assigning via columns, remembering to do it in gray code so I don't mess that up, right? So it's 0, 1, 1, 0. Or you could do it this way, which is 1, 1, 1, 0. Oh, yeah, thank you for calling that out. Yes, so as pointed out, this is the don't care row. And then I have the 1, 1, 1, 0 and 1, 1, 0, 0. They're both 0. Oh, the rows. Sorry, columns. Yes. Yeah. All right. So 1, 1 is this guy, 1, 1, 0, 0, and then this one is 1, 1, 1, 0. Wait a minute. 1, 1. Make sure this is all right now. Okay. And then, right, from here, it's just a K-map where you can do things like, that's a good one, that's a good one, and then this is probably just a wraparound. And then hopefully you're less out of practice than I am, and you go ahead and write that into expression, right? Which ends up being that's funny, there's a typo. And I have to figure out what that is. Okay, Q1. Let's do this one real quick. So in this one, we have, what is our not changing? So we have not B A changes, but neither Q1 nor Q0. And then Q1 is a 1, Q0 is a bar. Okay. My solution menu has a typo in it. All right. Right, and then here I just turned this into logic, which is a 1, 2, 3 input OR gate. I'm going off the map. With an and, right, and then I plug these guys into the AND gates. Ta-da! We built the output decoder. Does everyone get that? Okay, next state decoder, which unfortunately we're running out of time, but we can do the same thing. So it's at least worth drawing the K-map for this. So what we do is for the next state decoder, there is, remember that current state is actually going to have Q1 and Q0, which means there's actually two paths. There are two sets of logic. I need to do them separately. So the first time I go ahead and I'm going to look at the first bit of my next state decoder. And then I'll do this second bit, right? Do the LSB, then the MSB. I pick one bit at a time to write the K-maps for. But we care about the same thing, current state and input. And then we just say, well, what is our next state? Because last time we looked at what is our output. So now let's look at what is our next state. And more importantly, what is the first bit, our LSB of our next state? Well, it's going to be 0, 1, 0, 0. Same thing, we have don't cares in the second column. And then we have 0, 1, 0, 0. And then 0, 0, 0, 1. Right? And then we would do that K-map and write its expressions and draw its logic. And then we would do the same thing for Q1. We would draw its K-map, selecting the first, the MSB, right? Do that. Okay, so we'll do all assigned homeworks that have you do this kind of thing. We'll do K-maps to diagrams. I'll get the homework out. You can start practicing it. And then on Monday, we're going to do lab 8. So my plan is I don't have exact dates for when is what. I'll send them out in announcements. I'm going to be reducing the number of lectures and increasing the amount of time we spend in the lab room is my target, so that we can do lab 8, project 2, and project 3. So it's those, the homework, and the final, and then we're done, right? We're like a month out. Yay, right? We're almost done. I've got like a minute. Does anyone have any questions on?
Yeah, so we would design our two K maps and then do our two logic circuits from that. And then we would just connect basically the ends together as far as like, if we wanted to send it back, do like a 2-bit bus.
Yes. So, well, yeah. So this here is a 2-bit bus. That makes this, so NSD, really you could break it out like this, where it's NSD 0 and NSD 1. And then the current state, I can really just draw this. That's it without like any abstraction, right? Because they're just two DQ flip-flops. I need one D flip-flop per state bit. Does that answer it?
Yeah.
Okay, and so similarly, if I had 5 states, I would need 3 bits, right? Because I can't represent that 5th state with only 2 bits, which gives me a whole bunch of don't cares, right? Because I have 5 states and then 6, 7, and 8 are all don't care. Any other questions? So I guess finishing that off, right, this is, that becomes 2. That's 1, 2 comes there. And this even is 2 bits. And so the logic gets slotted into NSD and NSD1. We don't like wire them together, hardwire,
Yeah.
but we can combine them into the bus. Next time we do a lecture, which I'll see, maybe I'll lecture in the lab. I'm going to design something kind of very common, which is really just sequence detectors. So I can tell you, go ahead and design me something that detects the sequence 101. I want the output to say true if you see the sequence 101. And those are kind of interesting because you just start with the state because I've detected nothing, right? And I'm saying 101, so the first time that I see something, if it's a 1, oh, sorry, if it's a 0, I didn't start seeing that pattern, so we hang out. If I did see that pattern, let's move to the next state, right? Anyways, that's sequence detectors. We'll go make one of those pretty soon. And that's time, so have a good day.
So Monday, we're starting the next lab then?
Yes, we're gonna start lab 8 on Monday at State Machines. I want to start having you guys do stuff with that sooner rather than later so that it sticks.
And then Tuesday we'll be working on project 2.
I believe so, yes.